Hello, my name is Samuel Ripley, and today I am going to be giving a presentation on the application of hybrid modeling to the three-body problem. I was thinking about hybrid modeling and its potential uses when I remembered the three-body problem. The three-body problem has no general closed-form solution and must be solved case by case using iterative numerical integration, which makes it a great application for hybrid modeling. In this presentation, I will first give a background and overview of the three-body problem, explain its significance, and go over some of its applications. I will then go more in depth and explain why closed-form solutions have been found only in certain cases with specific initial conditions, and how solutions can be found numerically using iterative computer calculations at a large computational cost. Next, I will give an overview and explanation of artificial intelligence and machine learning, and describe how neural networks work. I will go over both artificial neural networks, ANNs, and deep neural networks, DNNs, and then I will explain how hybrid modeling works. Next, I will explain how hybrid modeling is applied to the three-body problem. I will go over the process of how an ANN is trained on a large database of solutions that are found by an arbitrarily precise numerical integrator. I will explain how the ANN then goes through a validation process as well as a testing phase, and I will discuss how well-trained ANNs perform in predicting the behavior of three-body systems. I will also discuss how neural networks and hybrid modeling can potentially be used for n-body problems, so problems that involve 4 or 5 or even more bodies. Finally, I will discuss why more efficiently and accurately finding solutions to the three-body problem is important and useful. So, starting with the three-body problem. The first known approach of the three-body problem was by Isaac Newton in his book Principia Mathematica in 1687, where he tried to determine if long-term orbital stability is possible for a three-body system like the Sun, the Earth, and the Moon. This is what the three-body problem is, trying to predict the behavior of a system with three gravitational bodies. The three-body problem has applications in a few areas, including astrophysics, the trajectories of spacecraft, and the interaction of black hole binaries with single black holes. The three-body system is very complex and chaotic. Slight alterations in initial conditions completely change how a three-body system behaves. This is why it lacks a general closed-form solution. However, for certain cases with specific initial conditions, closed-form solutions have been found. Apart from these special cases, solutions to the three-body problem must be found numerically using iterative computer calculations. This requires very powerful computers and has a large and unpredictable computational cost. To understand how hybrid modeling can be applied to the three-body problem, we should first understand the basics of artificial intelligence, machine learning, neural networks, and hybrid modeling. Artificial intelligence, AI, is the use of computer systems to mimic human intelligence. AI uses machine learning to imitate the way humans learn from experience. Machine learning, also known as ML, is when a computer system uses a large database to learn and find patterns in the data it is given. This is called training and is accomplished by algorithms. The computer system then uses what it has learned to try and predict what will happen in a new situation it is given. Neural networks are a type of ML model that are designed to imitate the structure of the human brain. They have a large number of connected layers of nodes that each receive an input and then produce an output, analogous to a mathematical function. All of these nodes working together result in a system that can function somewhat like the human brain, learning from experience, finding patterns, and predicting what will happen in a new situation it is given. Hybrid modeling is the use of machine learning models alongside physics-based models to create a hybrid system that combines the best qualities of both models, the speed and efficiency of the machine learning model, and the generalizability and reasoning behind physics-based models based on equations that model the physical world. Hybrid modeling helps to increase efficiency and speed, improve accuracy, and produce better results than either the physics-based model or the machine learning model would have individually. Machine learning is very useful in approaching the three-body problem because the three-body problem does not have a physics-based model that is complete. For the most part, each different three-body scenario must be approached case by case. There have been multiple studies on applying hybrid modeling to the three-body problem. One study, led by Shijun Liao, investigated how machine learning could be applied to find periodic orbits of three-body systems with arbitrary masses and then classify these orbits into different families. Another study led by Philip Breen investigated how a deep artificial neural network trained using a database of converged solutions found by an arbitrarily precise numerical integrator can quickly and accurately predict solutions at a lower computational cost than the best current numerical integrators. I will focus more on this study because it is more directly relevant to this presentation. Currently, solutions to the three-body problem are found by repeated numerical integration that is done iteratively by computers. Typically, for a given three-body scenario with known initial positions, masses, and velocities, the gravitational force is computed. And then the body's motion is approximated at some very small time later by calculating the effect on motion that the gravitational force has on the bodies. This process is repeated a large number of times to simulate the approximated motion of the bodies. However, for a numerical integrator to properly predict the behavior of a three-body system, it must be able to hold an exponentially growing number of decimal places in memory and use time intervals that approach zero. Because of this, arbitrarily precise numerical integrators are needed for the three-body problem, because they are flexible in the number of decimal places that they need to hold. One such integrator is called the Brutus integrator, which is especially useful because it's also capable of using time steps that approach zero. However, the computational cost of using arbitrarily precise numerical integrators, such as Brutus, can be unpredictable and is often extremely large. This is where neural networks come in. Once a neural network is trained, it can predict solutions to the three-body problem at a fixed and relatively low computational cost. In a study led by Philip Breen, a deep artificial neural network was trained using a database of 9,900 different three-body systems and their corresponding solutions found by Brutus, with an initially at rest equal mass particles in a plane. They used a feed-forward deep ANN, which was comprised of an input layer, an output layer, 10 hidden layers, and 128 interconnected nodes. The trained ANN then went through a validation process using 100 more situations with their corresponding solutions found by Brutus. After both the training and validation processes, the ANN was tested with 5,000 new situations, and its solutions were compared to those found by Brutus. The ANN performed very well. The solutions that it produced were very similar to the solutions produced by Brutus. It was also able to arrive at correct solutions very quickly and consistently. It took around 0.001 seconds, or 1 millisecond, on average, to arrive at solutions. This, on average, is around 100,000 times faster than Brutus. It also had a fixed computational cost that was very low compared to Brutus's computational cost. Another important attribute of any model of a physical system is how well it conserves energy. Because the three-body system is an isolated system, the velocities of the bodies should always sum to zero because their initial velocities were zero. Using this, the average relative energy error of the ANN was found to be around 0.01%. However, after adding another layer to the ANN, called a projection layer, the average relative energy error was reduced to around 10 to the power of negative 5%. Overall, the ANN performed extremely well, and it was able to quickly and accurately provide solutions to the three-body problem with a low computational cost. A possible next step towards more efficiently finding solutions to the three-body problem is a combination of Brutus with the ANN in a hybrid model that utilizes the advantages of both. This model would iteratively implement the ANN, but would use Brutus as much as possible because of its reliability and accuracy, and switch to the ANN whenever the computational cost exceeded the acceptable amount. Another possible use for the ANN is in n-body problems. This is explored by Asmund Sinevag in his master's thesis on how hybrid modeling can improve the simulation of the celestial bodies of the solar system. Another interesting study led by Veronica Ulibarena investigated how ANNs and DNNs could be used to create a hybrid model of the motion of planetary systems with a large number of bodies. Thank you for watching. God bless.